In this video, we are going to explore vector representation by going back and forth between two vector spaces, no matter how abstract the definition of our vector space may be. So as an example, let's start with something easy. So this vector v is 3, 4. I'm in R2 because I have two entries. I want to find two coordinates p and q that are not at the origin that also represents this vector. So it just has to have the same length, and it also has to, the magnitude, it also has to be in the same direction. So I could choose the point 1, 2 as the initial and 4, 6 as my ending point. This can represent this vector, provided of course that I am going in the same direction as 3, 4 would have gone. And that would be an easy check. All I'd have to do is check to see how far I went in the x direction, how far I went in the y direction, and the difference between those is I went in 3 in the x and 4 in the y. And so I know that these two ordered pairs could be the initial and ending point of the vector, not started at the origin. So that leads us to the definition of vector representation. Suppose V is a vector space with the basis of V1 to Vn, defined by this function rho of B, going from our vector space into Cn. And for every W in V, we define the column vector as the rho of B, being the linear transformation from V into Cn by this, where I've got the rho of B, rho B of W, V1, and rho of B of W, 2, V2, and etc. And this seems like what? Well, basically what it says is that we can write any vector W as a linear combination of the basis vectors of B. That's all it really means. And so the resulting scalars are just the entries of my vector of B, rho of B, rho sub B of W. A couple of theorems that we get out of this section at this point. It says that my function, this is just a function, that's how we're defining it. This function, rho sub B, is a linear transformation and it's invertible. Not only is it a linear transformation, but it's an invertible linear transformation. That means I can go back and forth. So if I'm going to go back to my other example. So if I let V be the vector 3, 4 in R2, find at least one vector representation of U. So we can go with our very easy solution by using our unit vectors E1 and E2. So V would be alpha 1 E2 and plus alpha 2, that should be alpha sub 2 E2, which we know would be our unit vectors and would be 1, 0, 0, 1, alpha 1, alpha 2. And then what we do is we put this into a matrix and augment on what I want the vector to be, which means I get alpha 1 to be 3 and alpha 2 to be 4. Okay, well that was easy. What about a different basis? Well, if we choose our points that we had, which is 1, 2, and 4, 6, as our basis, and all we have to do is make sure that these are linear independent, and we'll know that'll be another basis for R2. Then V has to be alpha 1 times that first vector, and then alpha 2, that's still alpha 2, times my second vector. And so what I end up with is augmenting on, so here's my 1, 2, 4, 6, and here's my vector. And then so that I have it as the vector equivalent would be alpha 1 would be 1, and alpha 2 would be 1. Alpha 1 would be negative 1, and alpha 2 would be 1. Now notice we didn't change the value of V, but we did change how we represented V. So I can represent V as the vectors 1, 0, 0, 1, or the vectors of 1, 2, 4, 6. That then leads us into a couple of theorems here. The theorem of coordination of linear independence. Suppose that U is a vector space with a basis B of size n. So I have S being U1 to UK is a linear independent subset of U. And it will be a linear independent subset of U if and only if, when R is going to be equal to the function rho of B of U1 all the way up to UK, is a linear independent subset of Cn. And then the next one I get is, suppose that U is a vector space of basis B of size n, then U is an element of U1 to UK if and only if my function of B of U belongs to my function of each one of those individual U1, U2. So I'm taking my basis here. So here's my basis of U1 to UK, and that U will be an element of this spanning set, the set spanned by this basis, if and only if I do this function, it will also belong to this function after I've done these, the function on the U1, U2, U to K. So let's take a look at an example. So we want to ask ourselves, is D, the set D, a basis for P2? Now, if we were in a different section, we would do something differently, but we know from the previous two theorems, we can choose a much easier basis for B, which is 1x and x squared. So that is all the polynomials. This is basis for polynomials of degree 2 or less. Now, to form a subset of C sub n that is really just applying my function rho sub B to each element. So I have rho sub B of my first element, rho sub B of my second element, rho sub B of my third element, which gives me this F set. And then because of the if and only if part, all we need to do is to row reduce this F, put it into a matrix, row reduce this F. And if we can row reduce it to the identity matrix, then we know this is linear independent, which means D is also a basis for polynomials of degree 2 or less. Now, this one's probably a much better one, but sometimes you want to have this one. So this example illustrates the broad notion that computations abstract vector spaces can be reduced to just computations in CM. So then, let's just go on and do, what does that give us, and do another example. So coordinatization principle, it says that if U is a vector space of the basis B of size n, then any question you have about U or its elements really depends on the vector addition or scalar multiplication in U, or it depends on a linear independence or a spanning set, and it all can be translated into the same question by Cn by the applications of the linear transformation of that function rho sub B to its relevant vectors. And once this question is answered in our complex space of size n, then the answers can be translated back to what it was in U, that vector space. And sometimes we may have to use the inverse linear transformation, and we know rho by the theorems and the definitions is an isomorphism. So we know they're it's bijection. So we know that we can go forward and backwards with our function rho. Let's do one more example here. So we have this set B, and it's a basis, and all we'd have to do is just to confirm it's a basis for P2. We want to find what the coordinates of this polynomial, which is negative 1 plus x, would be relative to this basis. Now, the coordinates of this on the basis of one of the most standard basis, which is 1x and x squared, would just be this. The way that we're going to approach this is that we would assume that this is a basis for P2, because they're telling us that, and so that we would turn each one of these into its equivalent vector. So this one is the vector 3, 0, 2, because I don't have an x. Next one is 6, negative 1, 4, and then the last one is 22, negative 2, and 14. Now I know that my polynomial, P of x, negative 1 and minus x, should be equal to alpha 1 times my first vector, alpha 2 times my second vector, and alpha 3 times my third vector, which gives us this augmented matrix, which rho reduces to this, which tells us that my coordinates of this relative to this basis, so the coordinates of this polynomial relative to this basis b here is going to be 1, 3, and -1. And so that's it.